Okay, good morning. Okay, we'll continue with the regression. So today, we'll just very quickly recap linear regression, polynomial regression that we covered last time, and then we start to talk about how we can solve linear regression in a very recursive fashion using gradient descent, and then today we'll talk about the second order methodology. And then we'll talk about regularization. We'll spend quite a bit of time on that. And then very quickly, we'll finish up with performance evaluation, which we kind of went through when we did the classification. Just will be a recap from that time. Just changes to the exam. So the exam will be very restricted in the window in light of what I saw in homework number 2. So this will be during between 9:30 and 10:45. I added 15 minutes before, 15 minutes after, just in case you want to start earlier or start later, but you will have only 1 hour 15 minutes within that window. Okay, still it will be online. You can do it from anywhere. This room is available if you want to come here. Yes, what's that? Either a graded scope or Canvas. So I'm looking into that. So most likely will be Canvas. Any question? Yes. Yeah, 1 hour and 5 minutes, 1 hour. Yeah, so you'll have 10-15 minutes extra just in case. Yes, I changed that. I saw in the homework number 2, many people are copying from each other. So now we have a very restrictive window. So hopefully this will make it more fair. So any question? You still don't have to be here in person, but I think this room will be available if you want to come here. And I will be online on Piazza if you have any questions during the exam. Question? Oh, yeah. But just in case for those who have a class before or after, they are more than welcome to use this room for the exam. Okay. Okay, so let's look at, this is the general linear regression model that we started with last week. And again, this is the model. This is the model. This is our prediction. And then X is our input data. So we did this, we went through it, and then we derived normal equations. So this is basically a closed form solution. If you have your training set in the X, and then in the Y, so the Y is the ground truth, the prediction, the true predictions for the input X data, then you can really calculate the model data, right? And then we said, okay, this will be a problem, especially if you have very large number of features, because taking the inverse of this matrix in here can be computationally very difficult, especially if you have if you have a large number of features, like capital P is very large. And then we moved from there to start to talk about polynomial regression. So if you have the same idea. So another feature space, so the relationship between the two spaces can be covered using a polynomial. And then once we do that, then we have our X transpose times X that we get the inverse of becomes E plus M choose N. So it becomes very, very large matrix. So we have to look at the gradient, the same as a solution to the problem, not using normal equations as we started with. And look at different ways how we can really do that gradient descent. And then these are different paths, any path, gradient descent. And the stochastic is we take at every round, we take just one sample, randomly from data. The batch one, you take the whole data at once, and then you update it. then the mini batch you divide the data into batches, and each batch is used to update the model at every. And basically, this is kind of the component that we went through last time. Okay, and then we ended up the lecture last time looking at basic from a different angle. We looked at this as a first order approximation. So we looked at this scalar series expansion, and we're looking here whether this is a reflection here f of a. So we are taking the evaluation of the function f and follow the series. So we have f of a, first derivative of f at x equals to a, and then the difference between x and a, and so on. So this becomes our evaluation. Then we take the first two terms, and then if we set the change in our theta to be equal to negative alpha and the learning rate and the data, to so this is the cost function theta. This is the change in theta and the derivative, the first derivative of our cost function. And then here we have the quadratic part, which is basically this part, the second derivative. So this is the second derivative, which is this capital H matrix. I'll look at it in a minute. This is the Hessian matrix. So basically we have this will be a P by P matrix. The diagonals in here will be the second order derivative of our cost function with respect to each one of the individual thetas. So this is the second derivative, this is theta 1. This is the next one will be in the diagonal axis, the second derivative with respect to theta 2, and then all the way until the last part in here. That's element, the second order derivative of theta with respect to theta 2. And then you can imagine basically what the row will be. The next in the element in the first row will be the derivative of L with respect to theta 1 and theta 2, right? And then and so on. And I will look at an example in a minute. But this is really basically nothing but really the third term, our third series expansion of a function. So now we have the change theta, and the change in theta, this transpose times theta, as if we have the theta square. And then we have our second derivative of our L, which is in the Hessian matrix in here. So before I come back here, this is basically just a refresher from calculus. The Jacobian matrix is our first order derivatives, right? That's what we looked at last time. And then the Hessian matrix is our second order derivatives. So look at this function here. See the derivative of this function. This is a multivariate function of x and y, but in calculus also you can make this composed of what? F1 and F2, right? So you will have basically more rows and more columns there. But for now, just like this is an F1, that's our purpose in here. And then, but it's really a function of x and y. Take the derivative of this with respect to x. You do that. What you will get? With 2xy plus y squared, right? Derivative of f with respect to y, you will get x squared plus 2yx, right? Now take this second derivative of f with respect to x squared. What will you get? respect to x. So take this one, the derivative with respect to x, what you will get? You get 2y plus 0. Second derivative of f with respect to y for this one, what you will get? 0 for the first one, and then I have what? 2x, right? Take the derivative of this with respect to x to y. What will you get? With respect to y, what will you get? So 2x plus 2y. This one with respect to x. Exactly. So what will you get? This with respect to x, that 2x plus 2y, right? So now you have the Hessian matrix, the diagonals in here. Second derivative of function with respect to x, you will get the 2y. And the second element in the diagonal axis, the second derivative of f with respect to y, you will get 2x. And then the other elements, basically, this is the second derivative, or the derivative of f with respect to x, to x and then to y. Then with y respect to, and then to x, you'll get the same value. So this is the Hessian matrix in here. But now, of course, when you program it for our data, it will be much larger than this in here. But this is just a refresher. But the idea in here, if we do that, so the concept is really much more important in here. So if you look in here at this manifold, so this mesh in here, basically is our 3D mesh is our data. This is the manifold where our data is coming from. If you use the Jacobian, the first order derivative, right? Then we are really approximating, at this point, we are approximating the function or the manifold as a hyperplane, right? But now if you use the Newton methods or the second order approximation, then we have this blue thing, right? So now when we are moving on this blue one, we are really very close to the manifold data, right? So our approximation becomes much better, right? So we are really hitting the local minima or the global minima much quicker and more accurately. Question? What's that?
What do you do after the second?
It becomes, the computational complexity becomes an issue, right? So even for Newton methods, the computational complexity becomes an issue, right? So now you have a trade-off. That's why basically most solution will stick to this one because it's much easier to train and get the solution. But this is more accurate, but it has its own problem as well. So always there's a trade-off in here. But it's very important to keep in mind that there is this solution here, which is the second order solution. Okay. But that's the whole idea behind it. It looks the math becomes a little bit more complex, but I really want you to always remember, write that down in front of you. To always remember, this is nothing but Taylor series expansion, second derivatives. So now they have the Hessian matrix because we have multiple variables. Why multiple? Because we have multiple thetas, right? Each one of those. So the x is theta 1, right? So the x is theta 1, the y is theta 2, right? You can think of it that way, right? So now, if you have two variables or two parameters in your model, this will be a 2 by 2. If you have p of these parameters, you will have p times p matrix in this case. Okay. So now, the good thing about this solution here basically is that it will get you to the global minima. So if it's a convex, it will get you to the global minima, and that's really one of the more attractive ways. So if you put this together in here, so we have an approximation. Go back here. Yes, let's see. So we have this approximation here, right? Of how we approximate our cost function using the first two terms, the LO and theta, and then we have the change. So this is the change. So the variable in here is theta 2, right? Or theta hat 2, or theta plus delta theta. We evaluate at theta, plus we have the change in theta times basically the gradient or the Jacobian of the cost function in here, right? We set basically, because we are looking at the gradient descent, we are looking into the opposite direction of the gradients, then we set this value here to be minus the negative sign because we're going to go the opposite direction. We have a learning rate, and then basically that direction is the derivative of our cost function at that theta. In the second order derivative, then we have to do the same thing now. We have this approximation, This is our approximation. So L f theta plus delta theta, first term as before, the second term as before, and now we have this new term in here, right? So now we have this new term that's basically involve the theta square. So now, one way to do that, how we can really minimize this cost function, we can take the derivative of this, right? The derivative of this cost function, and we equate it equal to a 0, right? So now, what we did before in the gradient descent, the first derivative equal to 0. This one, the same thing in here, but now the approximation is different. We have 3 terms in here. If we do that, what is the derivative of this with respect to delta theta? It does not depend on delta theta, right? So this one here. So this one here, this will be the same as what I have in here, right? Because delta theta is here. And now this is a delta theta square, right? So we'll have 2 times 1/2 the Hessian matrix times delta theta, right? So this is basically what we have in here. These 2 terms are the derivative. This one is the derivative of this with respect to delta theta. Derivative of this with respect to delta theta will give us this. This one, it doesn't depend on delta theta, so the derivative will be equal to a 0. Sorry? Square? Why? Because we have the transpose times the delta theta, right? Oh. Right? So that's basically, yeah. So it's because we're looking at vectors, it becomes confusing, but that's where the theta square is coming from. Okay. So now we equate this to equal to a 0, then we have delta theta is equal to negative the inverse of the Hessian matrix times the change in our L of theta, right? And now basically this now we found by taking the derivative of this respect to the theta equal to a 0, now we have an equation for our delta theta. What will be the change, right? So now we have the change, which is the function of the Hessian matrix, and now we put this all together, but we insert in here a learning curve, a learning rate, right? So the update for our parameters will be basically what we have as delta theta, right, from here, and multiplied by our learning rate. Compare that to what we had in the gradient descent, right? Where basically we have the learning and then we have the derivative of this. So we don't really have the Hessian matrix involved in here. So we introduce this Hessian matrix into our solution for the second order approximation. So not always invertible. And we'll look at that. I think I don't know if I'm covering that or not. Maybe a little bit, but not always. Yes, not always. Okay. Okay. Here's some of the problems with second order. If you start, for example, here, then you may go to this local maxima, right? You start to go up away from the global minima, right? So that's basically kind of a problem with when you have a concave local maxima in your data, and this happens. This happens. We don't have. I don't know. I will see if they will have it in homework 4. I don't think I have a problem on this. Okay. Now, as I mentioned before, it becomes really a little bit problematic when you have large P, right? Because you have to take the inverse. Again, same problem as we had before with normal equations. But it will give you really kind of, if you have a concave quadratic function, it becomes really very nice to solve. Okay, so now what we learned in regression, and these are the focus on the concepts. So we have linear regression. You can solve it using closed form solution using what? Normal equations, right? And now we can solve it using gradient descent. And now we can solve it using Newton's methods, second order, right? Gradient descent, we involve the Jacobian, the first derivative vector. In the Newton's method, we look at the second order approximation. We involve the Hessian matrix, right? Right. Basically, that's basically what we learned so far, right? And then the next thing we learned is polynomial regression, meaning that I convert my data from a certain space to polynomial of the feature space, and just to kind of look at the nonlinear relationship between my features. The problem with that, you can really easily do overfitting, as we saw some examples last time. And we'll look at some. Yes. Which one? Polynomial. Yeah, we did some examples last time. If I have time at the end, I can go through it. Okay. If not today, then on Monday. Okay. So basically, the polynomial, how does it work, right? I have an interface. I think I will have time at the end to go through it, and then maybe that will help. Will help. Just remind me, like that around 10:30. Okay. Now let's spend some time to look at some search methods, right? Before we go to the regularization part. So there is, if you look at the regression literature and some of the functions that are available in libraries, you'll see something like coordinate search, right? Instead of really doing this iteratively, you start from somewhere and then you start to look at each point, at each weight, you start to look into all the directions, right? In this case, you look basically east, west, north, south, and then you see which one of these four will move you into a lower cost function. And you move to the next one, you look at every direction, and that's basically kind of you can think of it as a kind of more of a brute force search. You can look at the coordinate, and then from there you start to find your way into the solution. An alternative one, which is not as exhaustive as that one, is basically you look at one coordinate time. So basically you look at your coordinate, like if you are in the x-axis, you only look at basically, do I go to positive or negative x? That's it. I'm not worried about y, right? And now I move to a new point, and now the next iteration, I look at the y. Do I go up or down, right? Right? I don't look at the x. And then I keep doing this zigzag, basically, kind of search in here. Of course, this is not as accurate as the other one, but this will get you closer much faster at the very beginning, as we'll see in a minute. So here are the two methods. The one on the left is the coordinate search, and the one on the right is the coordinate descent. These are only 20 steps. So you can see the coordinate search, because you are really at each step, you are looking at all directions and for all coordinates. You are moving smoother, right? But you are really much slower, right? Within 20 steps, the coordinate descent, yes, at the very beginning, it wasn't really as smooth as this one. You're not really converging to the solution quicker here. But in 20, you get to the solution, right? In 20 steps. So basically, you tolerate quite a bit of an error at the very beginning, right? But it's much faster convergence in here in this toy example. So these are two search methods that you will see in the literature about these. Okay, of course there's limitations in here because not really smooth, because you have that discontinuity. But I will spend more time about this regularization because that's very more attractive. Do you remember how do we do regularization and classification? What do we do? What's the concept behind it from classification? Whenever you hear I'm doing a regularization, what do you do? Just concept-wise. Because it's very important to have that concept very clear in your mind. What do you mean by doing a regularization? Just from the meaning of the the English word. So what's the close to the origin?
Ideally, we are doing a link to know what we try to do is we try to take like hypersphere and we try to have like the Lagrange multiplier, which kind of we either that we lost terms so that we kind of have a trade-off between them being closest to the origin as well as satisfying the block.
Thank you. So that's the technique, but I wanna zoom out a little bit. And what you're referring to is you want to constrain your parameters, right? You want to have some control over how much update you apply to your parameters. So in your example, for example, if you have L2 norm, I want to keep them as close to the origin as possible, meaning that I want to cap how big they are, right? Now, the L1 norm, right? We try to make basically some of them, or zero them out, right? So I want to make them zero, and that's basically exactly the same. Is the concept the same? The equations will look different from classification to regression, but it's really the same idea. All what we are really doing, we are adding. This is our cost function. Remember, up to here. This is our cost function for regression, right? Now we are adding this term in here, and this term is really the L2 norm that you are talking about. Basically, we are trying to include the magnitude of these parameters into our cost function. So now when we are minimizing our cost function, we are minimizing this error between the prediction and the true ground truth predictions. Also, we'd like to really minimize basically the thetas, right? Correct? So basically that's what they're trying. Of course, then the solution will be what? Theta equal to a 0, right? So now for this one will be 0, right? But that will not be the same thing in here. So you have that trade-off in here. To manage, the balance between really minimizing the error and reducing the L2 norm of thetas, we have this gamma in here, right? So this gamma is basically trying to manage. So this is a hyperparameter. How much do I need to balance between the L2 norm minimization and my regression cost function minimization? Does that make sense? So we have this parameter in here, right? Any question about this? I can replace this with anything. I can replace this with any other L1 norm or any other thing, and then that will give me some other way to regularize my solution. Okay, is the concept clear? That's what I refer to when you ask me what is the exam. I say like this, the concepts are really, really important. Because the mechanics, I can really change this and make it derive something, but it's, if you understand what you are doing, then it will not be a difficult solution. Okay, so this is a toy example. My true data is in red, right? And now if you really apply regression, I have this blue line, right? So it makes sense, right? Now, if I add noise, right? If I add noise to this point, it becomes here. I add noise to this point, becomes here. Then now my line is this, right? Now, another pair, I add a little bit noise here, another noise here, the line will change. Another noise, I move this one to here, I move this one, maybe it's the same. So I have this line. As you can see in here, as I change my noise, how much noise I add, my solution keeps changing. That's when we had discussion, I think, early on. What do you mean by generalization or robustness? We don't want, this is not really good, because now your solution, it keeps changing based on what kind of, how much noise you have in your data, right? So it's not robust enough. It's not generalizable enough. It's not general solution in here. Now, if I use regularization, ridge regression, we'll learn it in a minute, is the same data as before, right? And look at the solutions, basically. They don't really vary much. The slope of these lines, the variance among them is not really as high as the variance between the slope of these lines. Do you see that? So this one is good. This one is good in here. Yes, overall, you are introducing some error between your model and this one, but your solution, your boundary, right? Your decision boundary is not changing, right? Because remember when we did an SVM, you add another point, suddenly your decision boundary just changed quite a bit. That's not good, right? It's very biased in that sense. So that's basically what regression, ridge regression is trying to do. So this is just an illustration. You don't really want to overfit the data, right? So this one here, the green ones are the test data, the red ones are the training data points, right? So what we want is, yes, we want to have a robust solution, even if when you apply testing data, you will have some errors, because it's rarely you have your testing data is really as close as, as they're very close to the training data, right? I mean, they're from the same manifold, hopefully, but in real data, they are not always the case. Right? I mean, just imagine that you are really sampling data either from, medical or from autonomous vehicles or from any other application. The conditions, even if you do it in a lab settings, the conditions basically from one experiment to the next will not be exactly the same, right? So you try to make them look, they are from the same manifold, but they will not be identical, right? They will not be identical. So you always will have quite a variation. So you want your solution to be as general as possible, as robust as possible, and regularization is one way to do that, or the most common way to do that. So now, remember what we had, the gamma, this one. What is the gamma? The gamma is really kind of controlling. If gamma is 0, then I have the classical regression. If gamma is very, very large, then basically I'm doing what? An L2 normalization, right? I'm not really trying to bridge the gap between them. So what happens actually if gamma is huge, a very, very large number, what is the solution in that case? If gamma is very, very large, right? So basically this term in here becomes really very negligible, right? So what will be the solution? Is it 0? What's the other one? If you want to minimize this one here, right? So all the parameters will be very close to 0, or the average among them will be 0, right? You average them out, so the average among them will be 0, right? So you are reducing the average, right, among these parameters. So this is exactly what this example is doing. This is basically, you can look at it from here. We have the blue one for gamma equal to 0. That's basically linear regression as it is. When we increase gamma to 10, you have the green one. When we increase it to very large, it becomes basically what? It's just the average, right? We are reducing that average. Same thing in here. We go from 0.05, which is really linear regression as it is, not much of regularization. As we increase gamma in here, you start to see basically you are starting to have what? So just basically the average will become equal to 0, right? So your solution or your linear model here will become just the average among them. It's just a horizontal line. Any question? Yes. Of the parameters, yes.
Yes. What is the parameter need to hide? In the given chart, my points were on the vertical.
Yeah.
So I need M to be almost very high.
Yes, that's basically where you're playing with the hyperparameter, right? You will have different gammas, right? That's what hyperparameter is. Becomes a hyperparameter means you have to change it beforehand to the training and see what happens in the results, right? And that's basically where, in that case, the choice for hyperparameter becomes very important in that case, right? But you still wanna control it, right? This one is the cost.
Yeah, I mean, that is the original cost. This is the regularization. What should be you say hyperparameter, but like, what is the order of hyperparameter? How do we establish?
Yeah, this one is the hyperparameter. Oh, it depends on the data that you have. Like usually it like is 0.2, 0.3 roughly. That's kind of the most common ones. But it depends on the data. If you give me computational imaging data from some medical lab, right, that will be very, very different from computer vision, right? But in the computer vision side of things, this is very close to 0.2, 0.3 as a very common one, right? Because you are adding, you still want to give most of the optimization for this part. You are really having less control over, you don't want to constrain these as much. So you want to keep this less than 0.5, right? So you want to keep it a little bit low. If you start to make it more than 0.5, that becomes a little bit issue with the regression part. So you keep it less than 0.5. Yeah, but I mean, this is not compared to what you will be doing for the regression part. This is not really an issue, right? It's not a big deal. You have that parameter already in there in the regression, not because of the regularization, right? Okay. Yeah, my point is, if you are comparing two things, so if you do linear regression without regularization, right, you already have involved in already there, right? Now, if you add this to it, right, then it will not make a big difference in your solution, right? Oh yeah. If you use MNIST, it will be different, right? It's very much simpler. Okay. So now we go back and say, okay, now if we remember when we had L of theta equal to this term, now we add this term, take the derivative, and just put it into vector form, take the derivative with respect to theta, then the solution, this one what we had before, right, from normal equations. Now I have this one here will be basically gamma times theta, right? So this is the new term that I have. That's because of I involved this gamma in here, or this theta square, or L2 norm. Okay. Take this and equate to equal to a 0, and then find what will be the value for theta. So that will be x transpose x, what we had before. Remember this one? We had x transpose x inverse times x transpose times y. That was our normal equations. The difference between this and now and here, forget about the phi. The phi is just our polynomial regression, right? So in this case, you can just say it's just a 1. So what I have in here, I have the identity matrix, but it's scaled by our gamma, right? So now you can see your normal equations. What you are really, the only thing that you are already changing your normal equations is that you are scaling basically your this matrix here at x transpose times x, scaling it basically diagonally by this identity matrix, which has the gamma parameter, right? So that's all what you're already changing in your solution, right? So now you start to think about if gamma is equal to 0, right? Then what you have is just the normal equation as they are before, as they were before. If gamma is very, very large, this bit becomes meaningless, right? So this one here becomes is not relevant, right? So now all what you have is basically this identity matrix inverse times x transpose times y, and that's basically nothing but really you are averaging, right? You're averaging your data x and then scaling them with y. So this is the normal equation solution in this case. Okay. So this is the same thing for gradient descent. We are just really adding this term in here, right? And the derivative with respect to theta. So we'll have gamma theta over n. And basically this really becomes part of your gradient descent update in here. Okay. So now that regression, lasso regression, this is the term as before, but now we don't have the L2 norm. We have the L1 norm, right? You mentioned the L2 norm. We want to be close to the origin, right, of the thetas, right? But now we have the L1 norm. So the L1 norm means what? Means it's not really the square of the magnitudes will be equal to 0, which is the origin, but now you can have individual thetas go to 0, right? So now you could be on the x-axis, you could be on the y-axis, you could be on any of these axes for the parameters. So you want to, like, as if you're already making some of these parameters equal to a 0, some of these weights equal to a 0. Do you see that? So now this basically where the lasso regression will get us some sparse model compared to the ridge regression. So, and maybe you saw this already in some of your work. If you do regression or you do classification, some of those weights are really not 0 yet, but they're very, very small, right? Very, very small weights, right? This is basically trying to say, okay, just make them 0, right? It's just make them very sparse model, make this equal to a 0, and that makes a lot of sense from that perspective. This is just a experiment. You will see this in the homework where I have gamma in here, right? So gamma go from 0 to 4. And what I have in here is the coefficient values. I have 5 coefficients with this color coding. Now, if I don't really have any regularization, then these are the values for my weights. This is negative, this one maybe 0.4, and so on, right? See that these are the weights. As I increase my gamma, so if I put gamma equal to a 1, what happens in here, right? I have 2 of them, 2 weights became 0. You see that? 2 weights became 0. W4 and W2. You see that? It became a 0, right? As I keep increasing my gamma, all of them became 0, right? I'm zeroing them all out, right? Because as I increase my gamma, right? As I make my gamma larger and larger compared to the space of my data, this becomes basically negligible. Then the best solution for this to make everything equal to a 0, right? But on the way there, you will start to see the importance of some of these weights, right? So now if I ask you, which weights are really the most important ones, right? Or the least important ones, so the least important will be these 2, right? Right? Because they're already very small. As soon as we impose this L1 norm into our cost function, they collapse to 0. You see that? Yes. Yes. For real data, yes. This is just a toy example. Yeah, yeah, yeah. Yeah, roughly, yeah, yeah. So I'm, this is a toy example made up by hand, not in real life. So, okay. So now, if you look at using this for gradient descent, the same equation as before, take the derivative split to theta. Now, if you take the derivative of the L1 norm, then what you'll have gamma, then you have the sine, right? So that's the problem, right? You have the sine function, right? Because it's basically the absolute value of our theta. What is the sine function? It will be 1 if theta is positive or larger than 0, minus 1 is theta is negative and equal to 0 or 0. So we have this discontinuity happening, right? So we have this discontinuity happening in here. That's basically it's we'll see it in a minute. It's an issue that we have to deal with in here. So when you are really doing training and using lasso regression with the L1 norm, then we are really the learning rate becomes very important because you start to see things like become a zigzag. I will show you an example in the next slide. But that's where the learning basically babysitting the learning, the training is very, very important. Okay, so let's look at this example. This is a very, very famous basically experiment that explains everything. So I want you to focus for now on the upper left plot, right? There are two things. There is the background and there is the foreground, right? So now the background, what do you see? You see ellipses, right? You see ellipses in the background, right? So now these ellipses, right? These are the contours in here, ellipses of basically how the manifold is when you use only mean square error. We don't have any regularization. We're just using regression as it is, okay? And then what you have in this, you start from here. Forget about the yellow triangles. Just look at these white circles, right? Or white discs. This is our initialization. We are moving toward the solution, right? Only focus on the background, right? So this is the solution here, right? So this is we really move to that solution here. We don't have any regularization, right? We don't have any regularization. Now, this means that our gamma, so this white circles in here, our gamma is what? Is a 0. Okay? Now, if we make our gamma equal to a 1, and I'm using the L1 norm, right? So that then in that case, if I make gamma very, very large, right? So I'm ignoring my regression, right? I'm making my gamma very, very, very large. Okay? What I will have is the foreground, right? What will be my solution in that case? Will it be these diamonds, right? Remember the V shape in the previous one? So basically that's what we have. I have theta 1, I have theta 2, I have these parameter, I have this one, I have that one, right? This is the V shape. It all depends on the sign of my thetas, right? That's all what really matters. So I have these diamonds. This becomes my solution. So now this is at L1 norm. My gamma is very, very large, right? So now if I start at the same place, then very quickly I make the first theta 1 equal to a 0. Then I keep going all the way until I make theta 2 equal to a 0. This is my solution. You see that? Right? So these are the two extremes. The background is when I have only the gamma equal to a 0. So I have regression, I minimize the mean square error. The foreground, basically this is my gamma is very, very large. So I'm minimizing the L1 norm. I get here. Okay? You see that? If my gamma is 0.5, I think it's 0.5 in this solution. I still have theta 1. I have theta 2. Look at the background. Look at this. Yeah, they are, this background manifolds. The center, look at the shape of them. Look at the center. This was the solution, right? Because I impose now an L1 norm in addition to my minimization mean square error with a gamma of 0.5. This whole thing shifted. The solution shifted to be here. Do you see that? Now I start from the same initialization. I have the same initialization as before. This is my solution, right? So my solution went all the way, but it made what? Made theta 2 equal to a 0, right? And then it kept around this until it get to the solution. So now theta 2 is equal to a 0, theta 1 is, a little bit more than 1.5, right? Now remember when I talked about the discontinuity at the V, right? You see basically how it's jumping around here. That's because of that, right? So basically when you start to seeing something like this, then that's basically where the learning rate, how you have to play with it a little bit to make sure it's converted. Otherwise, if you are not really very careful with the learning rate, this could really jump around quite a bit and go to a local minimum. Do you see that? Do you see the difference between this one and this one? Any question? Yes. Okay, let me repeat. So on the left-hand side, gamma is fixed. So in both cases, right? So in the left-hand side, I have two diagrams. I have two solutions. I have two training happening, right? There is one in the background with these white circles. That's one training. In that case, our gamma is equal to a 0. Okay, so basically this solution here is the solution when I don't have any regularization applied to my data, to my cost function. So gamma is equal to a 0. Does that make sense? So I start here, and then I convert to the solution here after a certain number of iteration. So each one of these is my iteration. This is theta t plus 1 equal to theta t, right? So this is my theta 0, right? Theta 1, I mean, theta to the subscript, right? Not theta 1, theta, these are the terms theta 1, theta 2. But this is the first iteration, iteration number 0, iteration number 1, 2, 3, 4, 5, 6, 7, 8, and so on. See that? That's the iteration. Throughout the whole thing in here, all of them, gamma is equal to a 0. Now I have a second training where I have gamma is very, very large, right? So now what I am minimizing is gamma summation of the absolute value of the thetas. That's the L1 norm. That's my cost function now. And now I start here very quickly because this is L1 norm. L1 norm, what will you will zero your solution, zero out the parameters. Is it closer for it to go here or to go here? Here is closer, right? So zeroed out basically theta 1, which is on the x-axis first, and then it went up and zeroed out theta 2, right? And kept really moving around this region here, right? Jumping around this one, right? Now, these are two things. On the right-hand side in here, this is only one training, right? One solution. In this case, gamma, I think, is 0.5 in this example, or something over 0.4, but very close to 0.5. Does this make sense? Yes. Exactly. So basically, in the yellow one, gamma is very, very large. In the white one, gamma is 0. Okay. And we can do the same thing in the bottom part of the slide, but now we use the ridge, meaning we use the L2 norm, right? And basically back to what you just mentioned earlier, we start from here, right? So the yellow one, gamma is very, very, very large, right? Gamma is very, very large, right? So now very quickly we go to the origin, right? Why? Because exactly what you mentioned earlier, like to really minimize the L2, right? Norm, right? The summation of the theta square, right? How you just go to the origin right away. Now, if you look at difference in here, basically you have these circles in here. This becomes your solution, right? For the theta square, right? This is the L2 norm solution, right? The L2 norm solution are these basically contours in here, right? It was diamond in the L1 norm, is basically now it's the contour circles in the L2 norm, right? It makes sense because of the square, right? If you make gamma equal to a 0, then you start here, and then you convert to this solution in here, right? So basically it's almost relevant, right? It's very, very close to each other. The difference in the background contours, they are a little bit different, right? The shape of them are a little bit different because the way we are really doing our solution. Now, if you do the same thing now with gamma equal to 0.5, then basically you converge to this solution here. With the solution is different from the solution. So now L1 norm regularization or lasso and the ridge, which is the L2 norm regularization, they gave you different solutions. You see that? They gave you different solutions, right? Do you see that? So not necessarily they will convert to the same solution because they are the way you are shaping. Again, all what we are really doing, we are trying to make sense of what the shape of the manifold looks like, right? So now in here, this is how the shape on the L2 norm regularization came looking like. This is how it looks like in the L1 norm, right? So that's how our prediction of how the shape will look like. So, but different solutions in the lasso, theta 2 equal to a 0, and theta 1 is 1.6 or something like that. In the ridge, theta 1 maybe very close, maybe 1.65, but theta 2 is 0.25, right? It's not the same solution as before. Does this make sense? Any question? This is extremely important to understand the whole regression, topic. Yes. None of the weights. Yes, because that's the L2 norm, right? This is the L2, that's the red. So these two are the L2 norm, L1 norm, right? The L2 norm when we have the sum of the theta square, right? Magnitude square. Right, yeah, exactly. So if gamma is very, very, very large, right? Then the solution is just to make everything is zero, right? For the L2 norm, if gamma is very, very large, right? If gamma is very large in the theta one, eventually you'll get there, but you make one of them zero first, then you go to make the next one zero. You see that? Okay. Yes. Because now your L of theta, right? That's your cost function, right? That becomes basically your whole how the manifold looks like. That's where basically it's changing. The data is the same data, right? But our approximation of what the manifold looks like, it will change based on our cost function, right? Oh yeah, absolutely. Based on L of theta, the loss. Okay. There is this elastic net regression where basically combine both of them. So now you have the L2 norm with the gamma, you have the L1 norm with a gamma, but you add basically another scale, which is R, right? R, it will give you basically, are you more into, biased toward L1 or L2 norm, right? So you have both of these characteristic into your equation. So and this becomes another hyperparameter, this R, right? You want to have 50-50, 0.5, 0.5, you want to have 0.9, 0.1, and so on. This becomes another hyperparameter to get the best between the two words, right? Because what the idea behind it, for some of those thetas are really very, very small, you still wanna make them zero, right? Right? You wanna make them zero, but you are not really sure what is the threshold, right? So that will give you quite a bit of hyperparameter changes to the gammas. This one here, you try kind of to say, okay, the very, very small one will just make them zero very quickly, right? And then the rest will be for the L2 norm regularization. Okay. So this is kind of a very common elastic net regression methodology. Okay, performance measures. Basically, as maybe it's very obvious, different from classification. Now we are looking at predictions, right? We are looking at the values of the output function y, right? So we look at the mean square error, the root mean square, and the mean absolute error. And usually when you have to report, just report all of them, please, because each one of them is giving you a different idea. Another very common one is the coefficient of determination. Maybe you saw this in another class. The difference in here, we would like this to be equal to a 1 because this is 1 minus the ratio between these two numbers. The first number in here, look at the difference between your predictions and the ground truth, right? So now, how much you are different? So the average difference, right, or the average of the residuals between your prediction and the ground truth. That's the ratio to the average, basically difference, how far your data from the average, how far your data from the ground truth, right? This is basically the yi, each one of these ground truth samples, how far is it from the average of the y, right? Right. So basically the ratio between these two. If this one's in here is perfect, it's very, very small, then the r square will be equal to 1, and that's what we want in this case, right? Now, if r square is equal to a 0, that means this ratio is 1, right? If this ratio is 1, that means what? This is and this is are equivalent. That means what? Your best prediction is what? The average of the y, right? That's the horizontal case that we had before, right? Basically, that's the problem with that solution in that case. Okay, so you don't really want it to be close to 0. You want to be close to 1, as close as possible to 1 in that case. Now the validation, I went through this. So I'll go through this quickly again. I went through this in the classification. The training, validation, test splits. I went through this slide before. Take your data, split into train and test. The train becomes validation and train. The test is something that you never see in the training. The validation, you see it, you don't use it for training, but you see it to evaluate basically how good you are doing, right? The validation. So this is the same thing in here. And then you have your curves. Let's look at this two curves. I'm not sure if I did this in the classification or not, but it's really worth it to look at this. So I have two models in here, right? This is the training size. This is training set size. I have the root mean square error, and I'm using regression. This is linear regression. This is 10th degree polynomial regression, right? The blue one is my validation set. My red one is the training set. Same thing in here. The blue is validation. And then, as we said before, the classification, this will start very high and then it goes down. And then the training set will start very low and then goes higher as you get more data, right? Look at this one here. If you look at, they are converging, right? There are two things. They converge very quickly to a high error, right? But they converge very, very quickly, right? And nothing happens. It becomes very flat very quickly, and then nothing happens as you increase the data size, right? As you increase the training set, nothing really happens. You see that? Now, if you look in here, they don't really converge as quickly, but there is always a big gap between them. You are not really bridging this gap. You want this gap to be as small as possible. You want them to come very, very close to each other, right? So now in here, as I increase my training set size, it doesn't really have any impact on how these two behave. I have the high error, right? So this one here, is it underfitting or overfitting? Is the one on top. Is underfitting, right? So basically my model is not really, doesn't have enough capacity really to handle all the training data set, right? The one on at the bottom in here, because of the gap between them, right? That means I have what? An overfitting, right? I have quite a bit of degrees of freedom and capacity in my model, right? Basically, I'm not really trying to, it's kind of fitting to the training data, but it cannot generalize to the validation data, right? It's not general enough. So I'm doing an overfitting in this case. Yeah. Oh, yeah. It all depends on the data. As I showed you, the polynomial degree, the capital small m becomes a hyperparameter. I showed you the sinusoid right last time. Remember the sinusoid where the degree 1 and 12, they give you a bad solution. 1 is basically linear, 12 is overfitting. And around 3 or 4, I think, was the best solution for the degree of the polynomial. So it depends on the data that you're looking at. Okay. So there's so how do we do this? So we showed this in the sinusoid last time, so I'll not really go through it here. So there is two parameters. So there is the bias, there is the trade-off, right? The bias basically in here, how much bias you have. If you take your train a linear regression model more than once, and then each time you have a new set of data for the training, right? Then you would have certain predictions in this case. Now, the bias is the average prediction score of these models, basically how much. So in this case, if you have low complexity in the model itself, right? That means what? And my model is not really clever enough to look at my different training data sets. In that case, I will have high bias. I have the first training set that will give me some predictions. I have another training set will give me a completely different prediction. So I have a very high bias in that case. So it's very biased the training set that I have, and that's because my model is not really up to the task. It has low complexity. Okay, so that's one parameter. The other parameter is the variance, right? How much variation I have in my model. If you look between this model here, so in this case, if you look at all of them, they have the same average. Doesn't matter which data you are looking. The bias is very, very low. But if you look at the model in the red curve, compare this one to this one here, you can see from this one here is an overfitting, right? To really kind of tweak itself to the training data in this case. So now I have a very high variance, meaning that the model is very flexible, right? The model, as we mentioned before, like last time, the polynomial degree was 12 for our sinusoid. So try to go through every single point in my training data. That's really not a good thing. That's not generalizable, not robust enough. That's what's really happening in this model here. See that? So that's basically we have overfitting is very flexible, or we refer to it as high variance. What we are looking for, something like this. Imagine that I have the model capacity in here. You can look at this as the polynomial degree. Like this could be small m, right? That's my model capacity, right? Why not? then this becomes my bias. This becomes variance. As I increase my complexity, I have higher variance, right? But much lower bias, right? This is good, but this is not good, right? My complexity is very low. I have very low variance, which is not really good. I don't have any flexibility. But the more problematic is that I have very, very high bias. That's really, really bad, right? So you want to be something in here, something in where you have a trade-off between bias and variance. This is just another term that we use in this case. So if you look at our linear model, our high degree polynomial and low degree polynomial. So this one is exactly what we had in last time, the example for the sinusoid. This is degree 1, 3 or 4. This is 12 for the small m, right? So for the bias, when we have a linear model, it's very, very high, but the variance is low. When I had the degree of 12, the bias is very low, but the variance is very high. And then when we have a degree of 3 or 4, then I have my bias and my variance are both are low, right? So that's what we did in the example last time. Yes. If you add high polynomial with the regularization, right? Then yes, then it will, if you train it very well, if you have the right training data for it, then it will do it. That's the tricky part. Do you have the data for it or not, right? Okay. Yes.
I think along the lines of what you said, it's pretty obvious for a human to look at this and say the right clearly look at it.
Yeah, because we can plot it for this case, but for most cases we cannot plot this, right? Right? Because in this case we are assuming that we have theta 1, theta 2, just 2 parameters. That's our space, or even 3D space. Exactly. That's why there is visualization techniques where the t-SNE is one of them, and we look at this in homework 5 probably, where you can project your parameter space into a 2-dimensional space. It's not the best. It's using PCA basically. It's not the best way to do it, but at least it gives you something like this, where you can start to see where your data is in that 2-dimensional space.
Yeah, it just feels funny to me that the last step is have a human make the best judgment on if it looks over it. And that should be algorithmically.
It does. That's where the learning curves, right? That's where the learning curves. Well, I refer to it as babysitting, right? This one here. That's what when you're doing this, right? That's what babysitting this is happening, right? Either you look at this as epoch-wise, or you look at this as training, as you increase the training. And that's exactly what it is. This can be the epoch number, it could be the iteration number, or just training size. Because as you increase the training, right? This one, the ideal case, you want the error to be as low as possible. You want these to converge eventually as the training increases the size, and the gap to be very small between it. In that case, it's very good training happening. If you have this gap in here, and it doesn't matter how much you add, the gap is always like this. That means there is overfitting.
So you could find some way to project it onto 2D space with that and see that obviously.
Exactly. Then you will see that overfitting there if you can do that. This one is underfitting because you convert to a high error very quickly. It doesn't matter what you do for the data size for training. It's just the same as a plateau, right? So this was what I refer to as babysitting your training, right? You look at these curves, learning and validation, learning and validation.
Yes, what they correspond to each other.
Exactly, absolutely, absolutely. So this is definitely high variance because I have overfitting. This is high bias because I have underfitting, right? So all of these are related to each other. So this one here, this is just illustration of what these parameters are. Okay. So the error, and this becomes maybe in next level AI. We can really talk about this in more detail. But if you really want to model the error, you have the bias, which is basically the expected value of the difference. And then you have a expected value of the square of the difference, that's the variance. And then you have the error, which is basically the error in the data itself, right? You took images in a hazy day, like right, or rainy day. There's noise, you cannot see the it's there, it's fixed in your data. You cannot really model it. But I want to leave it as at this. This is the kind of the general error function that we could do. I put these links in here very quickly. I can go through it for the question that you asked before about like how this would look like, and then Salim, he just want to talk about homework 2 just for a few minutes. So let me just show you this. So you have the links in the slides. So you can go here. So if you have linear regression, this is where your data. You basically enter your, these are the x's, this is the y's, right? And then you fit a line. This is the equation. So this is 0.48x plus 3.5. So this is theta 0, this is theta 1, right? The R2 in this case 0.57. The mean square error is this 6.3 roughly. The root mean square error is 2.5. Okay. Same data, but you use the polynomial regression. And let's say degree 4, right? Then basically now you have degree 4. So you have these parameters. You have theta 0 here. You have theta 1. Theta 2 is small. Theta 3 is smaller. Theta 3 is 4 is much smaller, right? But the R2 is 1. It's perfect, right? This is a good solution here. The error is 0. The error is 0. You see that? So that's basically what you were asking for. If we make this degree 3, right? Now R2 is reduced to 0.9, right? And the error becomes from 0 to 0.6 and so on. So now if I make this 5 as an overfitting, I have very good, but look at these numbers, the coefficient. This becomes very, very, very small in here. If I make this 8, I don't know what will be. Oops. R2 is 1, but look at these coefficients in here, right? I don't have regularization in this case. I have only polynomial, right? So basically, if I have regularization, then I expect these ones to really put to 0, these two at least. Okay? That's what we were asking for about the earlier example. Okay? Do you want to do that? You can use my machine, so we just have like 7 minutes. I think just Celine, he want to just highlight kind of, the solution for homework 2. Thank you for doing.
So,
yeah, this is
So everybody, I want to point out that I know you had problems regarding while you are constructing the PDFs. So we have come up with another solution that you use where you use extension of Google Chrome. Please use that because it's much easier, and you will not lose any points because of these figures and stuff, and you won't have to deal with all of that by yourself. It will all do it as a long screenshot. Okay. So that's one thing I wanted to point out. The other thing, in this homework, most of you did very well, actually. One of the common mistakes was regarding the question 4. In question 4, while you were calculating the gradients, let me write it very fast here. So you had maximum for the hinge loss. I'm not considering the first part. For the second part, you had maximum of 0 and 1 minus yi x transpose wi minus b. When I put this below, it means that this is an array. So you had to take the gradient of this. So I have put the maximum. I have shown you, given you the formula for the derivative of the max function, right? The gradient of the max function. So what it was like so. The derivative of the max function was for 0 and g of x. It was derivative of g of x if g of x is greater than 0, and it was 0 otherwise. So you had to use this with this formula. Looking at this, what would you have? You would have, let me write it here. You would have, if you take the derivative of this with respect to w, what would you have? You have two arrays multiplied. You have a dot product. You would have the for w, I'm taking the derivative with respect to w. So we will have yi minus yi multiplied by x. I'm sorry, this should. When this is greater than 0, meaning that yi multiplied by xi transpose w minus b is greater than 0. So 1 is greater than yi minus xi transpose. So the 1 is greater than minus b. So this was what you had to do for W, for example. So for the B, you had to do the same thing and write the gradients accordingly. Let me show you the formulas in the code. I think this was the most common mistake. So here, here we see that, for example, we have the formula here, numpy dot x. Here x belong to x actually showed the index of the data sample, and you take the transpose of it. I write the opposite, but it doesn't matter because it's a dot product and you would have a scalar. So if you take the transpose of a scalar, you would have the same again, right? So that's it, minus p. So, and then you had to perform a standard gradient descent algorithm, nothing special here. I haven't put clearly this because you knew that you actually did this before the other questions, right? So this was one thing. And for the other thing, some of the people had problems constructing the ROC curves, these curves. So what you had to do was you had to select a number of thresholds, and then for every threshold, you would go and check for your every data sample, you would compare your probabilities of your data samples with your threshold. If your data sample's probability is larger than the threshold, you would assign it as 1. If it is smaller, you would assign it as -1, right? And then for every threshold, you would have a bunch of data, a bunch of probabilities, and your classifications. And then using these classifications and your ground truth values, you would have a true positive rate and a false positive rate. Then it corresponds to a point. One threshold corresponds to a point in your ROC curve like this, right? So a bunch of different thresholds would give you a graph like this. From these graphs, we understand that this is a correct classifier because the area under the ROC curve gives you the amount and actually describes how well your classifier is doing. So some of you had high accuracy values, but your graphs were not right? I mean, some of you had these problems. I was expecting you to understand that there was something wrong with your graphs and go over the code once again because your accuracy showed better graphs. I mean, supposed to create better graphs. This was another problem, one of the common problems. Apart from that, any other questions about the, go for it. Yeah, of course, the x actually, I have written it here. The variable x, the small x, corresponds to the index of the current data sample. The x, the big X, capital X, actually corresponds to your complete data set. The small x gives you one data sample in your data set, and you use it in the gradient descent algorithm. This was what I was trying to do. Yes? It is actually written at the beginning of homework 3. Yeah, it's very easy to use, and it's actually fun. There's something eating. I'm sorry? You have it in Canvas actually as a PD in a PDF format. I'm sorry? Locked. Okay. I mean, I can handle this. I can handle this right now.
Thank you.
Thank you.
Just for those who came late, I talked about the exam, so just make sure that you look at the lecture again. The exam window is only 1 hour and a half. It's not 12 hours. So you have between 9:15 and 11 to finish the exam. Okay.